Hi there. In this video clip, we will be learning some of the applications of PCA, in particular how dimensionality reduction and compression can be accomplished using PCA. So let's go through the steps first for dimensionality reduction. The first step is to compute the covariance matrix from your data. That's the sample covariance matrix. And then from your covariance matrix, you would compute the eigenvectors and eigenvalues. And this we have already seen before in one of the video clips, previous video clips. And then you basically order the eigenvectors and eigenvalues so that lambda 1 contains the largest eigenvalue and lambda d is the smallest eigenvalue. And the reason you do that is because you want to retain the eigenvectors which have the maximum variance, right? Because you know that lambda 1 represents the variance of the data along that direction, along the direction of u1. Yeah. And so we want to choose only the top k lambda ui pairs, right? I will come back to how that k can be chosen in a short while. So you would construct pk, which is basically just like p, but now you just consider the top k eigenvectors corresponding to the top k eigenvalues. And then finally you would transform the data xi by the transpose of p, right? And we already learned that that corresponds to a rotation which would align your eigenvectors, the eigenvectors along with your axes, right? And then you would get the projected values. The zi are your new features. The projected values are your new features, right? So your xi happens to be a column vector with size d cross 1 and your transformation matrix. It has k rows and capital D columns. And so when you do this product, you get zi, which has k cross 1 dimensions. So your data, which has d dimensions, is reduced to a vector with k dimensions. And that is why we say that PCA is used for dimension reduction. Now let's take a look at how compression can be achieved. And it should be borne in mind that this kind of compression is lossy, meaning that you don't recover exactly the original data, but there is some loss in the data. So how would you go about it? You would perform the same steps as dimensionality reduction. And so your zi would correspond to your compressed set of features. But compression, you need to recover the original data. So how would you do that? So to compute zi, we used the pk transpose. So now in order to reconstruct the original data, and you don't get back exactly the original data, you would get approximately the original data with some loss, right? So how do you do that? You multiply zi with pk. Pk has dimensions d cross k and zi has dimensions k cross 1. So when you do a product, you would get a matrix of dimensions d cross 1. But let's take a look at what is actually happening. So I have some points A, B, C, D marked here, and let's say those are the points of your data. And supposing u1 and u2 are the directions of your eigenvectors. Suppose u1 and u2 are your eigenvectors. Then note that in the direction of u1 there is more variance, and in the direction of the u2 the variance is much lesser. So one way to approximate it would be to project the points onto u1 and to ignore the projections on u2. Okay, so if you project the points on u1, you will get these points here, the circles. The original data are represented as cross, and the circles represent the projected data, right? So these points represent your zi's, right? These are your this is your compressed data. You could store it. See, in this case we are just considering, for example, two-dimensional data. Supposing you have two-dimensional data and this is your two-dimensional data, then I can compress it to a single dimension by simply projecting the data along u1. Okay, and I can ignore u2. But when I reconstruct it, when I get back R, I will not get back A, B, C, D. I would get only A dash, B dash, C dash and D dash. Meaning, note the points, the circles with the dots in the middle. So those are your new set of points, and the original set of points have been shown by your crosses, right? So the difference between them, that is your reconstruction error. So when you reconstruct your data, you get back only approximate values which are close by. Okay, and this also illustrates why we choose only the directions of maximum variance, right? Because the directions of smaller variance, like you could safely ignore them to some instant and store maximum information about the data despite losing the information about u2, right? Because that's just a small variance. u2 itself has small variance, and you can expect that the deviations along u2 would be very small, right, compared with the deviations along u1. So you could safely ignore u2. And as I mentioned before, the compression is lossy because you get a new set of points. Okay. Another thing that we should know, how to choose this value of k, right? How to choose the number of dimensions in the new data set, right? So k is the number of features you're going to retain, and you're going to ignore d minus k number of features, right? So you would choose a small value of k, which would minimize your reconstruction error. The smallest value of k which would minimize your reconstruction error, right? So how would you denote the reconstruction error? That is just the norm, the L2 norm of xi minus ri and the square of that. Okay, basically the squared sum of the deviations between the reconstructed vector and the original vector. Okay, so just need to choose a small value of k which will give you an acceptable reconstruction error. So that's the end of this video, this lectures, this series of clips on PCA. I thank you very much for watching.